Good evening, ladies and gentlemen. Pleasure to be here together, even if it's on a virtual platform. This occasion is a webinar by Professor A.R. Ravi Shankara on lose-win options. Are people in developing countries paying with their lives to climate change? This evening, we have our President, Professor Chandrima Saha, and we have the speaker of the day, Professor A.R. Ravi Shankara from the University of Colorado at Hart Collins, USA. A very warm welcome to Professor Shankara. To INSA fraternity, including the Vice President, Professor Devang Patel, whom I can see on the screen, Professor N.S. Raju from the University of Mysore, many fellows, scientists, faculty, and students, and everyone else who has chosen to be part of this event. There are faculty and students from the University of Mysore, the alma mater of Professor Ravi Shankara. On behalf of INSA, we officially extend a warm welcome to them all. There are people connected on the YouTube also. We also welcome them. I would invite President Professor Shaha to introduce our speaker of the day, Professor A.R. Ravi Shankara. Professor Shaha has been director of the National Institute of Immunology, New Delhi, where she has also served as Professor Emeritus till very recently. An immunologist of international repute, Professor Shaha has also been Vice President earlier. The Fellows webinar is a recent initiative from her at INSA that offers us to have some insight for some of the burning issues, international concern. I would request Professor Shaha to please introduce the learned speaker of the day.
Professor Ravi Shankara, INSA Fellows, distinguished audience, including Professor Thakkar, Professor Singhvi, Professor N.S. Raju, Professor Shamlal, and INEAS members, other distinguished people from universities, research institutions, and colleagues. We are actually been living under the shadows of this COVID-19 for the last 1.5 years. And the limitation of meeting face-to-face is the flip side of for some time to come, no doubt. So INSA started this Indian and foreign fellows lectures sometime back with the idea of bringing people to the interaction table in this series. And we are hearing today a very distinguished foreign fellow of ours, Dr. A.R. Ravi Shankara. Professor Ravi, as he is popularly known, is a university distinguished professor in the Department of Chemistry and Atmospheric Science at Colorado State University at Fort Collins, sorry. We have scheduled Professor Ravi earlier, but it was just at the beginning of the second wave, and the second wave struck and it could not hold his seminar. So I'm happy today that we finally hear him. And it would have been exciting to have him visit us, but for the time being, we have to float in the virtual world. Professor Ravi has worked over the past 4 decades on the chemistry of the Earth's atmosphere as it relates to stratospheric ozone depletion, climate change, and air quality. His science has contributed to deciphering the ozone layer depletion, including the ozone hole, to quantifying the role of chemically active species on climate, and to advancing understanding of the formation, removal, and properties of air pollutants. Professor Ravi Shankara has been recognized by institutions all over the globe. He is a member of the US National Academy of Sciences, foreign member of the Royal Society. He is a fellow of the American Geophysical Union, the Royal Society of Chemistry, the American Association for the Advancement of Science, and of the International Union of Pure and Applied Chemistry. His many awards and recognitions include an honorary doctoral degree from the University of York in the UK, Montreal Protocol Science Leadership Award, the Polanyi Medal of the Royal Society of Chemistry, the Stratospheric Ozone Protection Award from the US Environmental Protection Agency, the Silver Medal of the US Department of Commerce, Nass Robertson Memorial Lecture and Medal, and he's currently the chair of the Board of Atmospheric Science and Climate of the National Academy of Sciences. He is also a member of the Science Advisory Panel on the Climate Clean Air Coalition of UNEP and the chair of the advisory committee of the Vienna Convention Trust Fund. It is such a pleasure to have someone like him to listen to. The developing countries today face a dilemma, and this dilemma is constant conflict between development and health of the earth. Thus, the topic chosen today, the lose-win option, are people in developing countries paying with their lives to reduce climate change, is a very topical one, and we are all looking forward to his take on this intriguing issue. Dr. Ravi Shankara, please.
Thank you, Dr. Saha, for your kind introduction. And also thank you to Chandramohan Nachiyal and Seema Mandal for all the arrangements. They've been very, very helpful in making sure that this actually works well. Thank you. So I'm going to start sharing my screen, if I may. So what you should see is hopefully the, do you see the slides all right?
Yes, yes.
Okay, perfect. Okay. The title of my talk is kind of a mouthful. It's simply a way of expressing that when people do things in the name of development and things that we have to do, there are negative consequences sometimes. And in the process, we have to make compromises. And the compromises is what it's about in some ways. And then specifically, I'm going to be talking about what are called aerosols. This is suspended particulate matter in air. You all see it every day. This is the haze, you see, the pollution. And it also, for air quality issues, it's just called particulate matter. And in climate science, it's called aerosols. So aerosols, suspended particles in air. I just need to take a second to acknowledge the people who funded the work. When I was at NOAA, the NOAA funded a lot of my work, some of which I'm going to show you. And then NASA, which is National Aeronautics and Space Administration, funded some of the work I'm going to show you about for use of satellite data for deriving air
You want to
quality.
see in the WebEx?
I'm sorry? Pardon me, did somebody ask me?
No, could you please switch off your microphones? I think somebody was had the microphone on. So
Okay.
could you please switch off your microphones, please? Please go ahead, Professor Ravi Shankara.
Okay. Great. Okay. Now, you probably all see pictures like this. This is the action of human activities, the consequences of human activities. And the increase in greenhouse gases are one of the obvious consequences. If you were to go back and look at the concentrations of carbon dioxide, methane, nitrous oxide, these are some of the major greenhouse gases. As you can see, if you go back a few thousand years, it is pretty constant until about 1800. And then since then, it started going up. You kind of all know what happened around 1800. Starting in that century was the industrialization and larger scale agriculture. For nitrous oxide in particular, it was the development of artificial fertilizers and production of them, or Haber-Bosch process to make fertilizers. So if you look at the same thing, incidentally, if you go back and look at the data going back to 10,000 in this geological epoch called the Holocene, it's been pretty constant, all these concentrations. It's only now that's just going way up. I did not tell you the units, and you can see there are different units. Okay, there are units called parts per billion or parts per million. It's just it's very small, one in a million, one in a billion kind of thing. Okay, so if you look at carbon dioxide, more recent times, starting around 1960, going up to today, this is a very famous curve that was started by David Keeling at Scripps Institute of Oceanography. And essentially, what you can see is that it's constantly going up. Now it is well over 410, 417 parts per million is the concentration of CO. It also shows you there's very clear periodicity in how it changes. This is due to the uptake and expiration of CO2 from plants. So the same activities that lead to these greenhouse gases also lead to the aerosol particles, this particulate matter in the atmosphere. So these particulate matter, if you want to think about their size, think of like very, very fine beach sand. And it's something, if you were to take it in your hand and blow on it, it just blows away. These are of the order of about 100 micrometers, roughly. And if you have human hair, those of you, I don't have much of this hair, but you know, you probably can pull one of yours and look at it. And essentially what this hair is also the size of about 7 meters. Then think of this particulate matter that's much smaller in size. If you take PM10, this particulate matter of size less than 10 micrometers, you can put roughly about 30 of them around a human hair. And then it's the same way if you go even to smaller sizes, called PM2.5, then you can put another 15 of them around each of these PM10. You can just calculate this. The thing that happens though is smaller the particles, farther in your lung system it goes when you breathe it. Okay? So 10 micron particles stop somewhere around your throat mostly. And then if it gets smaller and smaller, it gets into your lung system. And finally, if you get to even smaller particles, they're called ultrafine particles, they essentially go into your bloodstream. Now, the size of these particles are also, this is why, incidentally, you have bad health effects when you breathe these particles. Now, the size also matters for another thing, and that is, depending on the size, the ability of this particle to scatter sunlight changes. And these particles, like 2.5 and 10 micron particles, are very good at scattering incoming sunlight. So that's why they affect the climate issue. So I'm going to kind of go over that a little bit more in a second. The key difference, though, between greenhouse gases and these aerosol particles, you have to kind of remember a few things. First, the greenhouse gases, or the ones we're talking about, are mostly long-lived in the atmosphere. They live for centuries, hundreds of years, decades. Methane lives for over a decade, and CO2 lives for a few hundred years to 1,000 years. Nitrous oxide for well over 120 years. And CFCs, depending on which one they are, also of similar magnitude. So they're very long-lived. The fact that they're long-lived also means if you keep putting it into the atmosphere, it stays there. It doesn't go away. Think of it as a bank account. If you keep putting money in your bank account, and if you don't keep taking the money out, you're going to just keep increasing the amount of money you have in your bank. And these greenhouse gases work on the climate system by absorbing outgoing radiation. I'll show you that in a second. And they do not directly affect health. Of course, they have huge effect on health indirectly by changing the vectors for diseases and various heat stresses and things of that nature. In contrast to the greenhouse gases, aerosol particles are very short-lived. If you put these particles in air, they live for about a week or two, and then they go away. So if you want to maintain a certain concentration, you can actually have to keep putting it. You kind of saw the effect of this. During COVID, when things kind of shut down, these things went away for a while. Now, because of their lifetime, they do not accumulate for long in the Earth system. But unlike the greenhouse gases, they actually scatter and absorb incoming sunlight. So, and they also affect clouds. So they're a totally different way of changing the climate system. But most importantly, they also directly affect human health. They also affect animal health and crop yields and all sorts of other things. I'm going to talk mostly about human health right now. Okay. And even in terms of human health, the metric I'm going to show you today is something called premature death, or premature mortality. It's just a proxy for health effects. This is just kind of tells you the number of people who die in a year exposure to particulate matter. Okay. A lot of people help me do this research. I want to note some of them who are my co-authors and papers. Jeff Pierce and Chandra Venkatraman from IIT Bombay, Jack Kudros, and all the other colleagues here. But in particular, I want to highlight the incredible role of Daniel Murphy, who's an amazing scientist who has been extremely helpful and extremely good at all these climate studies we have done. And he's just an expert at this. And also, Lichi David, who was a research scientist in my group at Colorado State University, and she just went to Utah State University. She's an amazing worker who has worked enormously in using the satellite data to deduce health effects and various other issues. She has done other things too, but those are the things I'm going to talk about. And all the things I'm going to talk about are essentially in these papers that are shown here. But I don't want to go into the details. So what I want to say is instead of looking at the bricks of the papers I mentioned, I want to paint a picture that you can see of how this works. Okay. First, just for a few of you who might not know what greenhouse effect is, again, I should apologize to all the experts who know all about this, that I'm going to simplify things tremendously in this process. And also I'll try not to show mathematical and chemical equations in here, okay? The greenhouse effect is a very simple thing. You all have experienced it. It is named after the greenhouse. If you have light that's coming in and it gets to this, let's say the soil, and it gets absorbed, and then it radiates infrared out. And if you prevent the infrared radiation from going out by having a cover on the greenhouse gets warmer. You have all experienced it. If you sit in a car with the windows closed on a hot, bright day, you'll see how quickly it gets hot in the car. Now, the aerosols, on the other hand, do something very different. The greenhouse gases, as I said, absorb outgoing infrared radiation. It is like they prevent heat from escaping. It is like you're putting a blanket on the planet so the heat can't escape. So it warms the planet. On the other hand, the aerosols actually prevents light, this energy from the sun, getting to the Earth's surface. So it actually tends to cool the Earth system. In addition to the direct effect of aerosols of absorb scattering radiation, they also change the cloud properties. So these are called aerosol indirect effects, and those also tend to cool the planet. there's actually one kind of aerosols that's pretty prevalent in India. It's called black carbon, which tends to heat. I'm not going to talk about it, but all the things I'm going to show you qualitatively does not change because of the inclusion of black carbon. Now, we need to kind of make these ideas into concepts that you can use for some of the calculations I'm going to show you. So my first thing I want to again emphasize, anthropogenic aerosols have lessened global warming. There's a concept called radiative forcing. It's a concept which you can think of as a thought experiment. Simply, if you were to take the Earth's surface, when it's in equilibrium, sunlight is coming in and the Earth gets warmer, it radiates heat out, and at the top of the atmosphere, the heat escapes. Incidentally, the atmosphere at the top of the radiative atmosphere is not the same as top of the atmosphere. So if you were to imagine if you're sitting on the moon and if you have an infrared thermometer and if you looked at Earth, the temperature is not going to be what's at the Earth's surface, but it's what is at the top of the radiative atmosphere of about 260 degrees Kelvin. Okay. Another is if you were to suddenly put a blanket or a whole bunch of greenhouse gases in here, it prevents the heat from escaping, and for a little while, the amount of energy that can escape reduces. That energy is used to heat the Earth system. This is essentially the greenhouse effect. But it can't go on forever, and eventually the Earth gets warm enough, it can radiate more and in slightly different energy bands, and then essentially it reaches equilibrium. But the time for it to reach equilibrium is very, very long. And during this time, incidentally, we are not going to be seeing equilibrium temperatures for centuries, even if you stop putting CO2 into the atmosphere right now. So this is kind of a issue of how do you deal with kind of a transient atmosphere. And I'm also not going to talk about that. Now, this is a picture that you probably all have seen. The radiative forcing, what I showed you here, is measured in a quantity called, it's a flux. It is in watts per square meter. It is the amount watts of square meter of radiation that has changed at the top of the radiative atmosphere. This is a picture you probably all of you have seen from IPCC. It has been horizontal, vertical, all sorts of stuff, all sorts of details in it, but that's not the important issue though. The key thing is there are so many things doing different things. When you add them all up, this is what it looks like. It's going back from 1950, 1980 to 2010, and it's even bigger right now. So that's the first point. And the second thing is there are things that are positive, there are things that are negative. Now, and how it affects is the total is all that matters. So remember this is a flux. The flux is the amount of radiation going out per square meter in watts per second. So what I've tried to tell you so far is greenhouse gases warm the planet, aerosols cool the planet. The net effect is what happens to the Earth system. So you have to kind of account for the greenhouse gases, we have to account for the aerosols, and actually we have to do something else, which is land use change, which I just mentioned briefly. And then you can calculate what's happening. The other thing to also note is that the aerosols, because they tend to cool the atmosphere, they have masked the full impact of greenhouse gases. In other words, if it weren't for aerosols, Earth's climate would have changed even more. Then we always come to the question, who is contributing how much to climate change? So this is a very common thing that you hear in the newspaper, you read about it. You see these kinds of pictures of, China is contributing 28% of CO2 emissions. US is 15%, India is 7%. And then you can add them all up. You can just see if you OECD countries, as developed countries together, about 35%. This is a very useful thing to know. But this just tells you what is being done today. But what matters to the Earth system is not just what we are doing today, but what we have done in the past also. In other words, what we feel today is a consequence of what we have done in the past as well as what we are doing today. That's the key thing to notice. So this is an extremely busy slide. So I'm going to kind of go this very slowly. First of all, please look at the bottom one. This goes from 1900 to about 2018. And this is the climate forcing. There's a radiative forcing in watts per square meter. It's going from 0 to 0.6 watts per meter square. So if you just redivided the world into 9 regions, you could do it by country, but it gets noisier. So the North America is this blue line. It has been keep going up. And then you can see other regions of the world contribute to this. If you look at this very carefully, you see all sorts of things that have happened. For example, if you look at Russia and Eastern Europe, this is the fall of the Soviet Union and how it changed. Then you can see the extreme rapid industrialization of China that you can see right here. Okay. And then there's a whole bunch of things. India, on the other hand, keeps going up steadily. It has changed over my lifetime by about a factor of 3.5, which is pretty much proportional to the population change in India. That's how much the climate has been the forcing has changed due to greenhouse gases. Now, if you were to then add to it the contributions of aerosols, the picture changes drastically. As you can see, when you add the aerosol contribution, going all the way up to about 1970, the forcing was not very large. It was actually pretty small. Okay, I didn't put the total here, it would have gone like this. Now, what happened here is 2 things. You can see when these things started breaking out in North America and Western Europe. There are 2 factors that lead to this breakout. One is because these areas were also health hazards, North America and Western Europe started cleaning up their air. So that reduced the aerosols. And the second is because I told you the differences in lifetime, you can't keep adding more and more aerosols to make up for the greenhouse gases. If you start adding so much greenhouse gases, think of it this way. If amount of greenhouse gas you'd have today is due to what was done last year, etc. But the amount of aerosol you have today is essentially what you have done today. So if you keep adding up the greenhouse gases, you have to exponentially increase the aerosols, which is kind of hard to do. So every country is going to break out at some point. And China has done that. China almost contributed nothing until about 2000, and it started going up. And in fact, you can see some countries even had negative values for a while, some regions. So this is the picture I want you to think about. And then I'm going to take this picture and put it into numbers. The way we do that is simply I took the same curve I showed you. This is the radiative forcing. And then this is the curve looks like it's not compressed because I want to look at what happens in the future too. Now, if you remember your high school physics, if you take a flux and integrate it with time, that is the total amount of energy. So that is really what matters. How much energy the Earth system has received and retained. is what all that matters. Not what is coming today, but the total amount. Okay, so you can do that by accounting for all this. Is one of the few equations I'm going to put. It is the energy gained by the Earth system that's both stored and radiated out is given by this equation. Essentially, I've added all the radiative forcing terms to gases and aerosols, and then integrated that from time T1 to T2, which is from 1900 to 2000. You can go farther back, and it doesn't change the picture very much. Think of it this in a very simple way. Essentially, think of it as a bucket. You have stuff coming in, and staying in the bucket or the bathtub or sink is not only what's coming out, but it's also what's going out or coming in, but also what's going out. This is a very big term, incidentally. Earth system is radiating out a lot of energy constantly. So what matters is what's left here, and that's what we calculate. Incidentally, we call this a new term, which is called cumulative radiative forcing. And then this kind of tells you what the effect is. It doesn't tell you where, how, and etc. It essentially tells you the global value, because that's all that matters. Okay. Now, this actually has some reason for doing it this way, because once you do these equations, if you were to use the linear equation, you can actually see what something called the net flux imbalance. And if you calculate that, that will tell you how the temperature is changing and also how other factors change. These are all global changes, not individual places. There are the way it expresses itself in different regions could be different. For example, the polar regions warm more than equatorial regions. That's true. But how much contributes to the global climate change, things such as sea level rise? This is global issue. The thing that I have not talked about is the land use, land cover change, which is essentially how deforestation occurred and how it changes surface albedo and evapotranspiration. I actually don't have time for it. I'm going to just skip it. But I want to put these energy terms in context because it's kind of important to get a feel for it. I kind of think about things in a very physical. The total amount of energy is the cumulative radiative forcing for the last 110 years is roughly 3 joules. Yottajoule is a funny, this yotta is a funny unit. It is 1 times 10 to the 24. If you're a chemist, you can think of it as roughly a mole of something. Okay. Now, total amount of energy we get from the sun every year is about 22.5 exajoules. So over the last 100 years or more, Earth has kept only 1% of the energy that we get from the sun. Again, just to get a feel for it, the total amount of energy consumed on Earth, electrical energy, is 0.0006 yotajoules. It's a very small number compared to the amount of energy you get. So this is the big number game where you can see how that system is being affected. So now, this is the slide that tells you how we can assign, if you want to say blame or responsibility or accountability or something. This is a very busy slide, so I'm going to take a couple of minutes to go through this. The dark curves are due to what has happened from 1900 to 2017 due to both CO2 and aerosol emissions. So as you can see, US contributed quite a bit, Western Europe about half as much, Russia and Europe, China contributed about quarter as much as US, and Indian subcontinent was both India and the neighboring countries contributed a little bit more, and you can see on and on. Now, this contribution up to 2017 doesn't stop in 2017. Even if you completely stop emission today, the contribution for 2100 is going to be this much. That's because the CO2 keeps accumulating and some of the energy it is also accumulates. Okay. So this is the total amount. Now you can also do this calculation using land use change, and that's shown here. So when you do this, you can see going forward in the next few decades, the largest contributor to climate change are essentially North America, Europe, and Russia. And you can add some of these other countries. India, Indian subcontinent, China have contributed not as much. This is actually a whole bunch of small states that have contributed as much as this. This is Australia, New Zealand, and Queensland. Okay, now the reason that it's worked out this way is the greenhouse gas effect has been offset by aerosols. That's the particulate matter pollution. Now you can also ask yourself what happens in the future. Oops. And that is shown here. Okay. Essentially, you can do it for a few different scenarios. I don't have time to go through this. You can think of 3P, this is called representative concentration pathways of 2.6, which is roughly what would happen, very roughly. Those cognizantists know that it's not true. It's the Paris Accord, and this is business as usual. And the scales have changed, and you can see if this continued, then US and Canada are still going to be large, and China is going to rival these countries. Okay? And India would still be small. Okay. Now, the thing to think about, though, is who contributed all these things? In other words, the developing countries developed by emitting greenhouse gases. Okay? And you can look at it. If you do it just as OECD countries, this is the easiest way to do it because this is the Organization of Economic Cooperation and Development. These are the developed countries. If you just do raw numbers, you see that the developed countries have contributed roughly the same as the rest of the world. And the economies in transition have contributed less than that. But if you normalize this to the population, you see the OECD countries, this is in an arbitrary unit, contributed so much more than the rest of the world. In other words, the OECD countries have gained the economic, made the economic gains by, of course, contributing a lot to the climate change today and up to 2100. Okay, so the bottom line of this is it's not just CO2. We have to think about other greenhouse gases and aerosols in particular are really important. The land use change and land cover changes, unfortunately, I didn't have time to go over. Some places it's already done, some places it's not done. If you had looked at the pictures from Europe, you'd see that it didn't change much because Europe forested long before 1900. On the other hand, Latin America has a huge effect. Okay, so my bottom line message is do not forget the legacy of emissions. It is not just what you are doing today, but what we have done in the past. Okay. Now, there's a disclaimer. This does not tell you who will be impacted by climate change, how much they'll be impacted, and to what extent they'll be impacted. Those are finite levels, calculations, and details one has to deal with. Now, as I said, these particulate matter also have this other phase of what I would call Janus, the double-headed god. They not only affect climate change, they also affect human health. Now, how much do they affect human health? So I'm going to look at India as an example of how this has worked out. The way I've showed you before is that these small particles, incidentally, the majority of the pollution in India is actually PM pollution. Ozone and some of the others are also there, but they're not as important as PM. But that doesn't mean forget the ozone. Now, if you inhale these particles, it goes into your cardiopulmonary system, the brain, it affects all sorts of things. And the epidemiologists really know a lot about this, and they kind of help with how it affects different kinds of issues and the morbidities and mortalities and various things. This picture is from my epidemiology colleagues at CSU, Johnson, Jennifer Peel, and they kind of simplified this, and it affects a whole bunch of things. That's the key thing I want you to remember. It affects your cardiovascular, brain, and various other parts of your body, and it stresses your system. Now, of course, I don't have to tell you what this is. It's a beautiful picture, isn't it? Blue skies, beautiful marble. You can see how clear it is. But I don't know how many of you have seen this Taj Mahal in this particular state. The last time I went to Taj Mahal, this is what it looked like. It's kind of beautiful in its own way, but I didn't see blue skies. I couldn't even see very far during my visit. It's in the Taj Mahal. So this is simply a manifestation of the particular matter pollution in a big chunk of India. Yeah. So now let's think about what it does, and let's try to kind of quantify this. If you were to go and take a satellite picture of particulate matter, this is from MISR, I think, satellite, what you see is something like this. It really matters, doesn't matter. This is something called aerosol optical depth. So when it's about 0.6, that means about 50% of the light does not get into the surface. You see that US, North America is pretty clean. It's mostly in the blue. This is China. You know where China is very polluted. And this is India. This is the Indo-Gangetic plain, and you can see various things. There are certain things that are not necessarily pollution per se. So, on the other hand, if you were to go and look at the way US used to be, then PM pollution in America, going back to this picture from the satellite images from 1985 to 2015, there's some more for 2020, which essentially gets it even cleaner, is essentially you can see that the darker colors have decreased. These things are in the units called micrograms per cubic meter. That's what the health people use. This, depending on different countries, the standards for bad is either 15 or 25, and depending on how long you breathe it, etc. It has been pretty bad in the 1980s. You could also look carefully, you can see the Los Angeles smog. And over the years, because of air quality regulations, the US has cleaned up quite substantially. But if you look at India, this is the Indo-Gangetic plain, this is a CF image, and you can see the pollution from space. It's just this river just comes right down this region, and you can see it very clearly. And of course, you all experience it, so I don't have to tell you about this. So the way you can do this is if we had lots of measurements at the Earth's surface over India of pollution monitors, we could actually do a lot. However, they don't exist. There are some in some cities, they're using, but for this country the size of India, is hard. We don't have as many monitors as we need. So what we did was to take the satellite data and then convert that satellite data to what the surface pollution levels are. So this just essentially shows you our calculated aerosol optical depth for the 6 regions in India. The regions we did it arbitrarily. It's called South India, Central India, Western India, Northern India, Indo-Gangetic Plain, and Eastern India. And as you can see, this is pretty large in the Indo-Gangetic Plain. It's about 0.5. It's annually averaged. And North India is much cleaner. And there's significant amount of dust, but dust doesn't mean it's natural. Okay. And there's also a certain amount of organic carbon, but a big chunk, as you can see, is actually aerosols of sulfate origin. So this is from burning fossil fuels, a big chunk of it. So this is how we try to calculate the ground level air pollution. And when you do that, these are the maps you get, but the color scales are deceptive. This goes from 0 to 200 micrograms per cubic meter. And just because it's blue doesn't mean it's clean. It's already well above the threshold at 50 here, as you can see. The green is actually pretty bad. Of course, during June, July, and part of August, you can see the monsoons clean up Indian Air. On the other hand, if you go from the dry seasons, January, February, then October, November, December, it's actually pretty polluted all over India. And this color scheme kind of exaggerates this. But don't forget, these yellow regions are also pretty bad, and so are the green regions. So once we have these numbers, we can calculate what's called the premature mortality. If anybody is interested, I'll be happy to show you how we do it. And this is the calculated premature mortality due to heart attack, strokes, COPD, and lung cancer. And then you can add them all up. Incidentally, the scales on these 4 are somewhat different, so you got to pay attention to this. And this is the total. So if I add this all up, we come up with a number that's roughly 1.4 million premature mortality risk due to this pollution over India. This is very similar to the global burden of disease calculation, or the number from Cohen et al. 2017. Please don't take it as really hard and fast numbers. These have uncertainties. And also the fact that you give this number doesn't mean you can identify who specifically died of this pollution. Okay? These are statistical numbers. It's the same way you can't just say somebody died of COVID. Usually people die of some organ failure. Now, if you just think about it and then look at the different regions, how this works out, you see the Indo-Gangetic Plain has a very large concentration of pollutants. And also it has a very large population too. And North India is, to the population, small, and the pollution is not all that small. So you can look across this for the different regions. You get a picture. The key thing though, what you need to do is something I'll show you in a few minutes, is called population weighted exposure. Just imagine if you have pollution in one place and the population in a different place, just because they're both in India doesn't make it bad, because these people are not exposed to this pollution. So you have to weight the pollution by population to figure things out. And then you can also figure out in different regions what are the different causes of this thing. And I have estimated, or we have not estimated, the economic cost of these things, missed days of work, other health effects, the other things people have to put up with, etc. As I said, we're using premature mortality risk as a metric for the health effects. But if you kind of do this annual mortality per million across the region, over India, it turns out they're not very different. It's, give or take a few hundred per million, and it's about the same. They're all about 700 plus or minus 150 or something, maybe 200. So it's almost the same. That says, wow, why is that the case? It's kind of interesting. Then you can ask yourself another question. Who is polluting who within India? So if you actually look at the annual mortality in millions for IGP, it's very large compared to some of these other regions. This picture is harder to follow, so I would suggest you look at this on the right. This tells you the fraction of pollution in each region that comes due to emission in that region. In the Indo-Gangetic Plain, most of the pollution in the Indo-Gangetic Plain comes from Indo-Gangetic. On the other hand, in eastern India, a big chunk of the air pollution in eastern India is not from eastern India. It is from transport from other parts of India and outside. Okay? And you can kind of see these variations. So these are actually kind of interesting policy ramifications, is that you can't completely control your air quality other than perhaps an IGP by making changes in your region. You have to have a pan-India approach. To sum this up though, I will just show you that for the that comes out of IGP, if you calculate it, roughly the premature mortality risk is about 500,000 people, out of which about 400,000 are in IGP and another 100,000 are outside of IGP. So IGP actually contributes to premature mortality outside of the region. Now, I'm going to just go into one other little area, because I actually grew up in a village for the first 10 years of my life. I've always wondered about how it would be for rural versus urban regions. And particularly, I want to call this non-urban for a different reason. What this shows on the left-hand side is the night light data of India. You can see the major cities. There's Delhi, okay, that's Calcutta. There's Bangalore, my hometown, Ahmedabad. I think it's Hyderabad, Chennai, etc. And also you can look at the population density from the Indian census. As you'll see, that there's a lot of population density even when there's not as many big cities. So this idea that the population is just concentrated only in cities is not a good idea. And also, you all are extremely cognizant of it. And that is, in India, the villages are not quite the same. The rural areas are not quite the same, for example, if you're in America. In America, go through Nebraska and you won't see a house every few miles. But in India, the villages are still concentrated. So I kind of use this population data and the night data, light data to parse out who lives in urban areas and who lives in non-urban areas. Then if you do this, if you look at the exposure of the number of people to particulate matter, this is what it looks like. This is across India. The two things to note is that this line here is the line that's given by WHO for the threshold for good air quality. This is India's threshold right here. Now, of course, you see that the majority of the Indian people are exposed to a lot more than the threshold of pollution. The thing that you hear mostly in the newspaper are these large values in big cities. Okay. Now, this is what you hear about. It reached so many hundreds, it actually goes even more than a few hundred micrograms per cubic meter. But there's a very large number of people who are exposed to these significantly high levels of air pollution. This is for the urban, the green is urban, and the orange is non-urban. It's kind of interesting that this is bimodality, and that actually, I'll show you, comes from mostly IGP. Then you can ask yourself, what about the region by region? As you can see, this is the picture I showed you before. And on here is the same thing for different regions. The IGP essentially is the real cause of this big second mode, and where the pollution levels are very high. The fact that these are lower in central India, eastern India, and down here in South India, etc., doesn't mean they're clean. They're still well above the threshold for even Indian standard. Only North India actually turns out to be pretty good, except for certain times. Okay, then if you do the population weighted exposure, this is what you get. You can integrate all of these numbers and ask yourself, is pollution really only an urban issue? And this shows you the annual mortality per million in different regions of the country, parsed in urban and non-urban regions. I suggest that non-urban regions are just as affected by urban regions in terms of this particular amount of pollution. It's not like you can just go away to these non-urban regions and be completely protected from air pollution. Now, if you do this another way, you can see the same thing. This is the annual mortality, again, for urban and non-urban. This is the fraction of population, urban and non-urban. And once you normalize it, it's essentially the same. Okay. Now, please don't think that the non-urban regions are getting all their pollution only from urban regions. The non-urban regions have their own sources of air pollution, significant amounts, residential burning, fuel burning, and some transportation. There are also industry, and agriculture also adds to all these things. We can talk about this. Incidentally, is emission inventory. This is the best we can do at this point. Knowing this emission inventory would be extremely helpful. So, what I've told you is that air pollution over India or developing regions helped mitigate climate change. It is not as bad as it could be, but it has been really bad for health. I just want to kind of look ahead a little bit. My first point is what's happening in developed countries is not new. This has happened before. Sure, you can recognize this picture. This is India Gate. So you know that this is India. You can recognize this picture. This is the famous Eiffel Tower. So you know this is Paris. Apparently, it was not too long ago. You probably can't recognize this picture, can you? Most people, this is, let's check China. This picture. It turns out this was Pennsylvania in 1948, and this is London in 1952. This place, we have had very, very, very bad pollution before. It is not new. We learned a lot of lessons. And of course, this local is important in dealing with this. Now, air quality problems in developed countries are really a big issue now. How do you deal with it? These are the questions I hope you all ask yourself. The thing that I want to note before I go to sum up my talk is air quality is not solved. You have to kind of manage it. I would venture to say even climate change, in a way, it's not going to be solved. it will be only managed. We have to evolve, learn, manage, and be accountable for what happens. So this is pretty much my bottom line. People in developing countries contribute less to climate change because of their air pollution, but have suffered more because of in terms of health. I showed you this climate contribution before. Let's look at the health burden, annual mortality from urban and non-urban in India compared to OECD countries and USA. This is for 2020. At least they're 3 times better off. And this is based on outdoor air. But remember that a lot of these countries also have other systems so that the air they breathe is probably much cleaner than these, what is shown here. Okay. So now I showed this picture before. Who is contributing how much what? And the big point I made is not only do you have to think about what somebody is emitting today, but you have to think about what people have emitted in the past. But if you look ahead, you have to remember who actually can reduce climate change going forward. The small emitting countries do as much as the big emitting countries. The only way they could do something even is by doing something like negative emissions. So, such as China, the US, European Union, and India, and Russia, Russian Federation, they do have to reduce their greenhouse gas emissions. So does the rest of the world. But when you start doing that, to do it in a smart way, so that not only do you reduce greenhouse gases, but also things that cause air pollution. Fortunately, the cause of both the greenhouse gases and air pollution are somewhat tied together because a lot of it is due to fossil fuel. And we're essentially burning the fossil fuel that was created over millions of years in a few hundred years. Okay, so this is the summary of my talk. The developed countries have contributed more to climate change to date than developing countries like India because of the greenhouse gases plus the effect of aerosols that offset the effect of greenhouse gases. PM 2.5 pollution in developing countries have reduced change, but those countries are paying a price in terms of bad health. Continued bad health is not an option in the long run. I hope you all agree that's true. And this whole thing, legacy is important. Actually, legacy, I did not talk about that for air pollution. Legacy in air pollution is also an issue. This contribution to future is what's avoidable versus contribution of the past is unavoidable unless developed countries can actually have negative emissions. In other words, they have to take out more CO2 out of the air than they're putting in. Is the technology available? No, but that's an interesting issue. I did not talk about a few other things going forward in developed countries, how simultaneity of clean air and development is a good goal. And as personally, I'm not a social scientist or an economist, I just feel like it can be done simply because I kind of think of the analogy of the telephones. When I was growing up, there was maybe one telephone in a block, and even that was not always working. And now everybody has a phone in your pocket. And that whole thing happened within a few decades. And just kind of leapfrogging is something one has to think about. The last thing, if I had a chance, I was going to talk about it. I don't have time and I don't want to, is people always talk about geoengineering to reduce climate change. I just want to point out humans have already done geoengineering in terms of air pollution. With that, I thank you for your attention listening to me. And I'm sorry I took a teeny bit more than I planned. Thank you to you for providing this opportunity to talk to you all. Thank you.
Thank you, Professor Ravi Shankara, for this wonderful exposition of the different aspects of this field, and for also clearing certain notions that people have about the situation. The role of PM 2.5 is really very, very important. And the unfortunate part is that the people who did not create it may also be suffering. The audience, I'm sure, has also appreciated the presentation. If there are any questions, please go ahead. Any queries or any questions?
Yes. I wanted to. I wanted to. Question is that the India is still using fossil fuels, and we do not have an alternate source. I mean, coming up very soon, so we will be using fossil fuels for quite some time to come. How much do you think that's going to affect India's, pollution situation?
It depends on how the fossil fuel is used.
Kindly unmute yourself, Professor.
Oh, no, can you hear me?
Yeah,
Okay. It depends on which fossil fuel is used. Some fossil fuels are much dirtier than others. For example, coal is much worse than natural gas. Okay, so if you were to use mostly natural gas or refined petroleum, it'll be much better than using coal. But of course, you need to produce electricity in a massive scale. How exactly that should be produced is an interesting question. Some countries have essentially gone away, are trying to go away from building more coal-powered power plants. Even China has stopped reducing coal-powered plants, and that's something to think about. India does use a lot of coal. If I'm not mistaken, there's a huge coal-powered plant being put up near the Bangladesh border very recently.
Yeah. Thank you, and such a wonderful lecture. I must say it's so informative and so interesting to know, because many of us who do not work in this field, this is really very enlightening lecture.
Thank you very much. Thank you for the opportunity.
But as Professor Ravi Shankara, you said, the area where we see a lot of pollution, the origin may be elsewhere. Origin of the PM 2.5 seen in an area may actually be coming from somewhere else. Now, how does one solve this problem?
An interesting question. I'm a physical scientist, so let me just tell you. Yes, I specifically showed you some plots of where the pollution is coming from. In air quality, at least in the Western countries, the premise is every state can control its own air pollution. Okay. That may not be true in India. I'm sorry, there's some echo. I have my apologies. So if India were to have an across India or a pan-India approach to dealing with this, that could be one thing. The second thing is air pollution. In trying to control air pollution, where I did not make this distinction, I should point that out. And I was talking almost exclusively about outdoor air pollution. So there's also the issue of indoor air pollution, how the indoor affects outdoors and outdoor affects indoors. So there is that issue of controlling one's own microenvironment to deal with pollution. So, for example, I forced my sister to have an air purifier in Bangalore. And I must tell you that the effect has been very satisfactory. She stopped coughing by using an air purifier.
Professor Raju, I have one question. Hello.
I'm sorry, sir.
Hello.
Professor Raju, you want to ask some question? Please go ahead.
Sir, in India, there is a concept of smart city concept. Smart city concept. They are giving the program for smart cities. Is going to lessen the contribute for the decrease this air pollution or this climate change? Contribute for the smart city concept.
I am not familiar with the small city concept.
Smart city.
Oh, smart city concept. Okay. Okay. So this is, yes, every step, in my humble opinion, helps. If the smart city concept, if I'm not mistaken, is how to use IT to make things work better, that's, I'm sure, is going to help. You know, you could think of lots of interesting things, right? For example, if you were to have a traffic that flows, if you focus only on the cities, a traffic that flows smoothly is going to do lots of things in addition to reducing pollution. It actually makes people spend less time on the road. It will increase the fuel efficiency. It can do all sorts of things. So the question is, how do you do it? That's probably what smart city concept comes in. I do not know. The other thing, for example, are very cost effective that I've seen in other countries are solar water heaters. If you have been to Israel, it's I think almost required by law. Everybody has a solar water heater so that they don't have to burn any wood or do anything to heat their water. And once you start with hot water, it's much easier to cook. So there's a whole bunch of things that could be done, I would imagine. But you are there, and I'm sitting so far away. Your local knowledge is essential for solving India's problems. And doing it the Indian way, but not necessarily doing what somebody else is doing.
Professor Singhvi has a question.
Yeah. Sir,
Thank you.
sir,
I'm not sure. I'm not sure how secure is your estimate of pre mortality.
Premature mortality.
The premature mortality with 2.5. What are the causal connections?
Yeah, that's actually the vulnerable underbelly of those calculations. There's few different things that, first of all, I told you before, and I'll tell you again, they're not very certain. Okay. But the reason the uncertainty comes is manifold. There aren't actually very extensive epidemiological studies in India. These numbers used the known epidemiology in other parts of the world. So if somebody were to ask me what would be a very good thing to do in India, it's a massive epidemiological study like that has been done in the US and in Europe for the Indian conditions. So that's number one. Number two, you know, the details, the physiological factors are not very well known, how things work. So these are statistical numbers. And to be able to say any certainty, even maybe I shouldn't even have put a second place. I mean, for one thing after decimal place. The significant figures to go. It looks like it's within a factor of 2 or 3, they're reasonable. But if you look at the exposure curves, you know, the epidemiologists have done a lot of this kinds of sensitivity analysis. My biggest concern in the calculation I showed you is all these epidemiological studies come from a different part of the world. We're assuming that's applicable to India. Thank you for pointing that out. That's a very important point.
Thank you.
Dr. Pradeep,
Pradeep has a question.
Yeah. So thank you, Professor Ravi Shankar. Since you have gone into so much detail, I was just looking at your one slide where you compared Pennsylvania, London, and today's India. Now, do you have any field, I mean, because you have done in such great detail, that what did Pennsylvania and London do right so that they have now cleaner air?
Yes, I don't want to start sharing green again. If I could, the emissions of pollutant causing stuff have been reduced tremendously. You know, it just has been reduced by about a factor of 50 in those places. In Denora, of course, that in Pennsylvania, there's a very simple thing. There's a copper smelt. No, it might be, it's a smelter, but I can't remember if it's copper or zinc. And they had to shut down those kinds of industries. And that's one thing, that really important lesson. There are usually some very significant pollutant sources that do a lot of damage. So if you identify them, if you can get rid of them, that helps a lot. That's number one. Number two, you just have to keep improving your emission controls and emissions. India did a great thing in going to changing the cars to the essentially almost the EU standards, and that should help from the cars. But the rest of the things, I'm not sure about trucks and buses and all the other things. But in terms of regions, I don't want to focus only on urban regions. The non-urban regions, for example, if you were to pave roads nicely, that they stay intact for many monsoon seasons, it will reduce a lot of your dust. Dust in India is usually resuspended rather than something that blows off. As a big chunk of it is essentially dust that comes from human activities.
Thank you.
Actually, that reminds me to tell you, you know, this is where the local knowledge is so essential for dealing with the problems of India. So I hope other people in India pick up and start doing more and more. There are lots of wonderful scientists doing this kind of stuff. So if somebody were to ask me, what would you suggest? I would definitely suggest India should do an assessment of its own air pollution using Indian scientists who are working in these areas.
any more questions? Professor Shamlal, you would like to clarify something?
Very wonderful lecture, and he is expert in this field. So very, very nice, detailed information. My question is one that he, in the last slide, he said development without GHGs. That's where is the problem. So once you burn either coal, which is, of course, dirty, but even the petroleum, of course, carbon is there, so CO2 will come. hydrogen, methane will come. So without GHGs, it's very difficult with the fossil fuels. So we go for, let's say, other energy sources. So what is your suggestion in that?
I know, as I said, I'm not a social, Shyam, you know that I'm not a social scientist. I'm not an economist. Okay, so I don't know how feasible these are. So the thing that I would say is, to me, India showed something absolutely fantastic about the ability to leapfrog when they did in IT and what it has done to India, its economy and the way of life. Okay. Now, centralized systems are not necessary or even wanted. India is blessed with enormous amount of sunlight, and India is blessed with enormous amount of wind, especially during some seasons. Okay, I used to fly kites, and I know the seasons where it works extremely well. But anyway, my point though is that a combination of, and also India is of a size where it can actually have smart grids. So that's number one. If you kind of go through electrification, a lot of the problems are going to get better quicker. The beauty of an electrical motor is it doesn't emit CO2. Maybe India should reconsider its nuclear program. Again, nuclear reactors don't emit CO2. There could be other issues, but that's a decision one has to make. So, and the other thing is that India still currently has about 1 billion people who really don't expect the electricity to come on when they turn on the switch. Okay? So the kind of expectations of reliable electrical power is also different. So that's something to consider in doing this. So microgrids, smart cities, better roads and transportation, all of these things, I'm sure would be one way of thinking about it.
Professor Singhvi, you have a question.
But thank you.
Professor Singhvi. Professor Ashok Singhvi, your hand is raised.
I think it was the previous, you didn't take it
Yeah,
down.
it was.
You didn't take it down.
Already.
Professor Shamlal wanted to say something.
Very good. Thank you very much. Nice.
I'm sorry, I forgot to bring the hand down.
Down.
Earlier, I forgot to notice that your hand was raised. Sorry. Thank you so much for all the questions, and thank you, Professor Ravi Shankara, for this wonderful of the session. For the formal vote of thanks, may I invite Professor Devang B. Thakur, the Vice President of Science and Society, Indian National Science Academy, and I would request him to please propose the word of thanks. Thakur, please.
Thank you. Thank you, Dr. Nautiyal. It's really my pleasure to convey thanks on behalf of INSA to Professor Ravi Shankara for this really insightful and informative talk on particulate matter and its impact on climate change and human health. We're really grateful that Professor Ravi Shankara, an absolute authority on the subject, agreed to give this lecture. Thank you, Professor Ravi Shankara, for this really very nice lecture. I would also like to acknowledge the efforts of Professor Chandrima Saha, President of INSA, for starting this webinar series, which celebrates the 75th anniversary of the independence of India. This series has gained a large public audience because of outstanding speakers like Professor Ravi Shankara, and of course, it is being streamed on YouTube, so a lot of people can watch. Several staff of INSA have played an invaluable role in organization of this lecture, and I would like to extend my thanks to them. They include Dr. Arora, Dr. Nautiyal, Dr. Zokarkar, Dr. Seema, Mr. Karthik, Mr. Aditi, along with several other staff members who have worked behind the scenes. And finally, and of course, most of all, I want to thank all of you who came to listen and participate in the discussion. Thank you all. And everyone, please keep safe.
Thank you.
So with this, we bid
you.
goodbye.
Goodbye. Goodbye.
Goodbye, everybody. And we will announce the next lecture